talking to you today about whether you should use a database or a stream processor for your real-time application. The agenda is going to look something like this. It's going to be about me. So in other words, why you might want to pay attention to what I have to say. The difference, what is a stream processor? What is a database? What are some common use cases for real-time applications? So that we'll get a sense of like, okay, is it obvious I should use one or the other? What does it look like underneath the hood for a stream processor and a database? And then lastly, we're going to help you place your order. You're going to make the choice of technology. So let's get into it. Hi, I'm Almog. I'm your chef de cuisine for this kind of experience. I've worked on stream processing and kind of real-time applications for the last decade, give or take. I've worked on early generation stream processors like Samza. I've done some work on Kafka. I had a brief tenure working on Pinot actually at StarTree, and most recently I co-founded a company called Responsive that works in the stream processing space to kind of make those applications more efficient, reliable, and easy to operate. So I do have a slight bias, so obviously take that into account when you're listening. But I think there's definitely kind of good use cases for all of these technologies in their own place. So you can see a list of kind of more of the open source technologies that I've worked on here on this slide. As far as the actual content, let's hop right into it. So what's the difference? I'd say there's kind of one really important takeaway, and that's the interaction model for a database and a stream processor. The way that I like to think about it is that you pull data from a database, whereas a stream processor gets data pushed to it. So the interactions look kind of like what you see on this slide, where in a database, you issue some kind of query, you formulate what it is that you want to see, and then the database kind of answers that question and returns the data to you. A stream processor, on the other hand, you formulate the application in a way of saying, no matter what data comes to me, I want to process it in this very specific way. It's kind of a very structured way of writing a query, and you write it once, and from that point on, the data gets pushed to that query, and the query emits kind of incremental results of the execution of that query. In kind of words instead of diagram, a database can query the same data in many different ways using some kind of structured query language or maybe a domain-specific language. There's a very simple kind of client-server side interaction with the way that you interact it. So this is nice because the database can be hosted like in StarTree with Pinot, and then you as the client, all you have to do is issue queries and get responses back in a very structured fashion. These kind of 2 points really lend to the database's key strength, which is its flexibility. You can answer many different types of questions. You can have many different types of applications all interacting with the same set of data. A stream processor, on the other hand, it actually supports arbitrary code logic. So there might be things that you can't express in SQL. I think a kind of very typical thing here is the ability to interact with other systems. So for example, if you want to make an RPC from within your stream processor, that's kind of a little harder to do within a database. You usually have to do that in your client. Or you may want to integrate directly with downstream systems. So you take some data from a stream and then you want to put it into another system like a database or a data warehouse or something of that sort. And I think the one word that I would use to describe a stream processor is structured processing. So compared to the very flexible processing of a database, a stream processor is very structured. You code it up and that kind of contract is all written in code, and you'll keep executing that one code on a loop every time you get a new event. So moving on, how do these technologies implement this these kind of query patterns that they make available to their clients? On the left, you'll see the database, and on the right, you'll see a stream processor. And kind of the key takeaway here is that the flexibility of a database requires it to have a few more moving parts. As you can see here, there's a client, which usually runs kind of outside of the database. But the way that it interacts with the database is through a centralized node that's usually called a query planner or a broker or something of the sort. Pinot has this kind of broker service. And what this service does is it translates that SQL query into something that the database knows how to execute. Then the broker will delegate the actual execution of those tasks to what's often called like a data segment or a searcher or a kind of a database processor. This will actually fetch the data, usually parallelized across many nodes, filter out the data that's not necessary, aggregate it if required, and return that all the way back to the broker that aggregates the responses for many segments, sends that back to the client. Similarly, in order to be able to kind of have all of these processes work in as flexible way as possible, you will typically need something like a metadata service to organize, okay, what nodes, what data segments are online, which is the broker that's currently the leader, and you'll need to have a metadata service that coordinates all of this. And the last thing is you need a separate ingest. So the client typically is doing the reading in these types of real-time databases, but you'll have a separate service that ingests data into the database. So as you can see, there's kind of lots of moving parts that make a database functional in this very flexible manner. The benefit is that all of these are typically individually scalable. So if you have a ton of data, you can have lots of segments, but you might not need necessarily a very kind of robust metadata service layer, or you can have a slightly smaller broker if the query volume is a little lower and you have high data volume, high data kind of storage needs. A stream processor, on the other hand, is kind of quite simple. Really, most stream processors have one processing task, and I'm talking specifically about kind of Kafka streams. And the state is typically embedded. Responsive as a company gives you the option to externalize that state for a little bit more flexibility, but most stream processors embed that state because the type of processing that you use is really quite straightforward. You read an event, you look up the data associated with that event, and then you output it. So the downside of this is that obviously this is much more structured. You can't really individually scale the processors and the state in most open source stream processing solutions. So that's kind of the architectural trade-offs. Let's move on to kind of one side note. There's a class of technologies that are called streaming databases. These kind of play a middle ground between two of them. Typically, their use case is to use a stream processor for the ingest and then a database for the query side. And they package that all up into a single technology that allows you to kind of keep these views incrementally updated. I'm going to put this away for the rest of the talk, but if you're curious, here are two examples that you can kind of look into and see how these streaming databases work. Onto the use cases, right? You're building real-time applications. What are the kind of things you might want to do with them? Let's kind of start by looking at how each of these technologies describes themselves, specifically Pinot and Kafka Streams. Pinot describes itself as a real-time analytics open source platform for lightning-fast insights with effortless scaling, cost-effective, and data-driven decisions. I think the key thing to notice here is that it's really about lightning fast and it's really about analytics. It's so squarely kind of meant to solve those problems. Whereas if you look at the Kafka Streams description, you'll notice it targets a very different set of use cases. Specifically, you'll see that it builds itself as a library for building applications in microservices, where the input and output data are stored in Kafka. It combines the simplicity of standard Java with the benefits of Kafka's server-side cluster technology. So I think there's a lot to unpack in there, but the kind of key parts here is the first is to notice that it's meant for applications and microservices, which is a slightly different use case than the analytics realm. It's a little bit more in the transactional operational realm of applications that you might want to write. The other thing that's kind of obvious is that it requires the input and the output data to both be kind of interfaced through Kafka with the rest of the world. So that's a certain limitation. And then again, I wanted to point out the fact that you can write standard Java, not just SQL, which is where kind of most databases land. So that's how the technologies build themselves. What are some use cases? I'll start with one that kind of lands pretty squarely, I think, in the stream processing use case. The example you see here is from Salesforce. They basically have a bunch of stream processing jobs that look at topics and then transform those data and put them into other databases or warehouses for serving. So in this specific case, each one of these different stream processing apps is reading a topic and extracting some features. So it's doing some computation to compute what those features might be, and then it puts it into another database for serving, typically for building some kind of ML models or doing some feature refinement for real-time serving. So those ETL pipelines are pretty squarely, real-time use cases that you might want to implement with a stream processor. On the other hand, something that fits pretty squarely in the database realm are interactive dashboards. The key characteristic of a dashboard is that typically the user who's using it wants to have some kind of exploratory power in order to determine the views that are shown to them. So for example, in the who's viewed your profile in LinkedIn, which is powered by Pinot, you want to be able to filter by, how what the company is, or some interesting viewers, the time frame, and all of these have to be computed on the fly. So the kind of idea is going back to the earlier slide I had, where the database allows you to really flexibly view the same data in many different ways. So this would be extremely challenging to kind of deploy and operate as a stream processor. So this fits pretty squarely in the database realm. Going into one more that fits kind of pretty squarely into the stream processing realm is microservice orchestration. So this is a real-time use case where microservices kind of function, they interact with one another instead of through RPCs, they interact with one another through an event bus. And this event bus is typically implemented on something like Kafka, and then each of the applications are written with stream processing as their backbones. You might want to do this for various reasons. Typically, it's because of the transactional kind of guarantees that you can get from such an ecosystem. Where the real-time event bus gives you the ability to reprocess events, make sure that if you fail, you don't commit the data that you haven't actually yet processed, and you get these really kind of reliable semantics in your microservices, which again is not something that's typically a good fit for an analytics real-time database. So those were some use cases where I think it's a little bit more straightforward which one you would use, but it's not always that straightforward. There is a good chunk of overlap in the middle, and I think one of those use cases is kind of a use case for real-time alerting and aggregations. And this is an example that comes from a responsive customer, Metronome. They do kind of usage-based billing. So what they do is every company that is their client will submit metrics to them. They'll aggregate these metrics and compute invoices for their customers' customers, so their end users. And this, they actually use both stream processing and databases. The stream processing part kind of cleans up and does the real-time aggregations of the data that's coming in. So one thing they do is they do duplicate. So if their customers submit multiple billing metrics that are duplicates, they'll filter that out for them. That's something that, again, if you go back to that original slide, is very structured. Right? You can kind of do this in a database if you wanted to. You could deduplicate the data, but it makes kind of a lot more sense to do this incrementally instead of recomputing the duplicates every time you do it. So that's a great use for stream processing. Then they do some basic aggregation that is, again, very structured, right? The billing metrics are well defined, so they can aggregate this in a very structured way. They finally put this into a database in order to serve to their clients the use cases, some alerting, so on and so forth. And that's a much more interactive use case that their customers will have in order to be able to interact with their product. Similarly, a similar kind of use case, but slightly different, is the use case for anomaly detection. I would say while the real-time aggregation and real-time alerting is a little bit more structured in the sense that you have like a very well-defined, structured aggregation that you might want to do, anomaly detection might require something a little bit more complicated. So, for example, for each event that comes in, you want to be able to query it using perhaps more complicated aggregations. You want to be able to query lots of different views of the data. Depending on the customer, depending on the event that's coming in, you might have more or less complicated requirements. So this is an example here of how DoorDash was using a database, specifically StarTree's a Pinot, kind of in Third Eye, in order to do this kind of anomaly detection. Every time an event comes in, it's processed through Pinot in order to get the to detect whether or not it might be an anomaly. So this is a great use for a database. Simpler anomaly detections are often written in stream processing jobs. So if you have like a deployed ML model or something like that, and all you need to do is call that ML model from your streaming application, that's a great use for a streaming application. So to summarize, sometimes the use case is clear, right? In stream processing, you'll see data pipelines, you'll see microservice orchestration. In the real-time databases, you'll see these interactive dashboards, you'll see things with like data exploration, but there's a little bit of a messy middle. And I promised you that the rest of this talk would be helping you figure out what to do about this messy middle, when to choose stream processing, when to choose a database. So in order to figure this out, let's get a little technical. We're going to look underneath the hood about the kind of performance and the architectural distinctions of the two technologies. So let's start with the performance profile. We'll start with latency. Databases like Apache Pinot, they're really optimized for ultra low latency on indexed queries, right? You can get easily into the single digit millisecond queries and get your answers very quickly. Now, this is true for indexed queries. If you have these like unindexed query use cases, they can be kind of a medium to high latency, but it's really great to be able to combine these two, where you have your kind of production workloads with these indexed ultra low queries, and then you have your unindexed queries for your more like exploratory use cases when you're exploring what data is available for you, so that you can, in development particularly, find out what indexes you might want to build. Kafka Streams, on the other hand, gives you a very consistent consistency latency profile, and it's a little configurable. But if you want ultra low latency, kind of similar to what you might have in a database, you typically sacrifice throughput. And the reason for this is that most stream processors work in kind of these commit intervals where they'll process some data and then they'll commit that data. If you're using transactional guarantees, which is typically what you would probably see from a stream processor, using in like transactional use cases, you don't actually see the output data until you commit. So in Kafka Streams, for example, the default commit interval is 100 milliseconds, which means that if you're even if you can process each individual event in single digit milliseconds, the output is not going to be shown for around 100 milliseconds. So this is something to consider. If you really need that, like, single digit or a millisecond responses, you might want to consider a database, because otherwise you'll sacrifice your throughput in your stream processor. On the other hand, if all you care about is very consistent latencies, the stream processing workload is probably going to get you the most consistent processing that you can have, because there's no increased load when there's more queries coming in. And I'll get to that later in the degradation model. So this gets you to kind of your ideal workload. The kind of optimization profile. Had a little glitch on the slide there. In a database, a lot of the optimizations happen automatically for you. So if you're kind of issuing lots of different types of queries and you don't want to optimize each little individual one, a lot of the optimizations happen for you in a database off the hood. In a stream processor, typically there's only very minor kind of topology optimizations that you can do, but you have a lot of room to manually tune your application. So you can tune all the code and all of it to really get the performance profile that you want. So it requires a little bit more investment, something you wouldn't want to do in a flexible use case, but you can really tune a specific use case to hit a certain kind of performance line that you might want to do. The latency bottlenecks are also different. In a database, typically disk I/O is one of the biggest bottlenecks. Then query planning and indexing. So making sure that you have kind of effective indexes in order to serve the queries, which is what I mentioned earlier. In a stream processor, the latency bottlenecks are a little different. The serialization is the biggest thing, because you're just reading so much data in and pushing so much data out constantly that the serialization becomes the biggest CPU bottleneck. Similarly, there's operator chaining. I mentioned that there's like these commit intervals where you'll only see data after a certain amount of time. The more of them you chain together, the more this latency kind of bottleneck compounds. So if you have 4 or 5 stream processors backed up one after the other, you might introduce a significant amount of latency. So kind of playing around with those trade-offs is if latency is important to you, you might want to consider those. The last thing that I think is also very important to kind of determine whether a database or stream processor is right for you is the degradation model. In a database, what you'll see is typically dropped or timed out queries. So under load, you'll see situations where the kind of database cannot serve a query. And this kind of makes sense in a lot of situations, right? Like if you're issuing a query to see a dashboard, you don't really want to display that dashboard 2 minutes later when someone's navigated off your site. Like at that point, serving that query is pointless. So you might as well drop it or time it out. In stream processing, on the other hand, the degradation model is called lag. So instead of slowing down or canceling processing an event, that event will just be processed later. So that way you can guarantee that all of the events that you're seeing are going to be processed at some point or another, independently of the load on the system at the time now. So those are two very different degradation models that might define how you want to kind of create your application. Moving on to some architectural choices underneath the hood. This is a little bit more about understanding the technologies, so that when you make your choice, you can kind of know whether the architecture fits what you had in mind. Storage for a database, especially in an analytics one like Pinot, is going to be columnar, and it's going to be replicated within the database. So this allows you to do two things. One, it allows the database to be the source of truth, because it's going to be online and it's going to be very, very extremely available. So that can be delegated to some managed service, and you can have very high availability just through that. The columnar aspect of it lets you do very kind of efficient aggregations across many different keys. Contrast this with a stream processor. A stream processor typically has row storage data, which means that you can search up the value for a specific row very effectively, but scanning many rows becomes very ineffective. So this is really optimized for this like incremental compute that stream processors do. And similarly, the storage is typically externalized. So instead of storing multiple copies of the data within the database, you store it somewhere else, like in Kafka for changelog topics and Kafka streams, or S3 snapshots for something like Flink. For compute, you'll see kind of different models of parallelism and caching. On the database side, you'll see parallelism at the query level. So you'll be able to parallelize your queries as you kind of get more of them, and that's the unit of scaling. Similarly, caches typically aren't used. So if you have a workload that issues the same queries very frequently, you might want to consider a stream processor, which on the other hand uses caches very heavily and parallelizes based on the partition. Partitions are kind of the internal unit of processing. So it's kind of a little bit less flexible in how you scale. So you want to make sure that you have that partitioning set up ahead of time. Similarly, in the networking, you're going to see kind of data shuffles in the database, where you're going to see kind of persistent data shuffles through repartitions in a stream processor. The differences that you'll see here is that in a database, if you're querying lots of different data, it makes sense because you want to only shuffle the data that you need. Whereas in a stream processor, it'll optimistically shuffle the data. So your network costs are going to be different depending on whether you're seeing the same data over and over again, or whether you're processing new different types of data. That could kind of really change the networking cost equation for a database in a stream processor. And lastly, the way that you want it to be deployed. Typically, a deployment of a database is going to be centralized, whereas a deployment of a stream processor is going to be embedded into your application and depend only on Kafka. So that's kind of the different architectural choices. So let's kind of get to the pinnacle of the talk. How do you choose between them? What are you going to actually place your order when you have to make a choice? Order a database if you need query flexibility. I think that's the kind of key word that you might want to have. Interactivity is important to you, especially at super low latencies, and you don't have any transactional requirements. You want to order a stream processor if your processing is very well defined. You can process the same data in the same way very frequently. Or you might want to do it if you need to express business logic beyond SQL, or as I mentioned in the degradation model, you prefer lag to failed responses. But that's not quite the whole story. Why not order both of them? And in fact, this is frequently what happens in many real architectures. You don't use just one or the other. And Kafka and Pinot really work together. They were designed kind of both at LinkedIn. They both integrate very well with one another. And you can push different parts of your architecture to Kafka or different parts of your architecture to your real-time database like Pinot. And this is how your architecture would look like if you did that. Typically, you have some kind of source data. It's either CDC'd or directly pushed into Kafka. You have your stream processing to filter and pre-aggregate that data so that you reduce the costs on your database. And your stream processor can also drive any like event-driven notifications and these kind of push use cases that you might have. And then the database powers the interactive applications. And I think these slides will be shared afterwards, but I have some kind of examples and links to where you can see real world examples of companies using both of them in tandem to serve their applications. All of these actually come directly from StarTree's use cases. But as Uber detecting kind of app crashes, DoorDash is doing the anomaly detection of fraudulent kind of deliveries and order requests, and also Stripe's powering of the transaction dashboard. All of these use both stream processing and a database in order to kind of really build a high fidelity experience to the end customers. So that's it. Thanks for listening to my talk here, and definitely feel free to stay in touch. I would love to chat with you in any of these forums listed here. I'm happy to answer any questions.